I am Dr. S. Balaji from Chennai, India, doing my invited scientist work at Suncheon National University at Suncheon. And for the past 2 years I am in Korea, and nearly I am going to complete my period. And the topic of my research is mediated electrochemical oxidation process. The topic of the presentation, the current presentation, is mediated electrochemical oxidation process, determination of rate constants for the destruction of phenol in batch and continuous feeding modes. Next, please. First, I would like to give you an overview of the process mediated electrochemical oxidation. This is an emerging and innovative process and innovative technology for the destruction and decontamination of organic compounds like persistent organic pollutants and other materials like dioxins. And it has been well known in the Western countries, and particularly United Nations recommended this process as one of the promising future technologies for use in developing nations. And the major advantage of this process is it is being operated at ambient temperatures, that is less than 100 degrees, and at atmospheric pressure, 1 atmospheric pressure, normal. The final products of any oxidation of any organic is, the final products are only carbon dioxide and water. That is, the organic is totally mineralized to carbon dioxide. And in our laboratory at Suncheon, we have designed our own electrochemical cell for cerium oxidation with a good efficiency. We have tested the applicability of this MEO process for different organics in the batch and continuous feeding modes. Next. And this is the overall process or the experimental setup, we can say. This is some bench scale experimental setup we have developed. And this is the very important core component of the mediated electrochemical oxidation process, that is electrochemical cell. This cell is very important. This is having an anode and a cathode separated by a Nafion membrane. And in the anode part, the anolyte, we call it as anolyte. Anolyte part, we have cerium and nitric acid solution. On the catholyte part, we have nitric acid. And during oxidation, cerium-3 is converted to cerium-4. This cerium-4 in nitric acid medium acts as a very powerful oxidant, and this oxidant is taken to another tank, a continuous stirred tank reactor, where the organic is fed from another tank, and here organic destruction takes place. So, and we also pass some quantity of nitrogen to take out the carbon dioxide that is produced. And this is some scrubber to effectively oxidize any volatile organic carbons. And finally it is condensed, vapors are condensed, then the final product CO2 together with nitrogen is taken out, and some moisture is scrubbed. Then it is the final product CO2 is analyzed, and this is the vent gas. And in the catholyte part, it is also equipped with the scrubber to effectively capture the nitrous oxide vapors. Next slide, please. The objective of the present study, the present investigation, is to study the destruction of phenol by batch and continuous MEO process, to evaluate the kinetics of batch process, to model CO2 evolution pattern during organic destruction in continuous feeding mode, to match the CO2 evolution pattern between model and continuous process experimental data to find the best pseudo first order K parameter, and to calculate the thermodynamic parameters of organic destruction process. Next. And this shows the experimental conditions. As I told you, anolyte means the solution which is in the anode side of the compartment, in the electrochemical cell, where we take cerium-3 around 1 molar and nitric acid 2 to 4 molar optimum. We take 1 molar cerium-3 and 3 molar nitric acid, and 2.5 liter is the total volume of the solution. And during the cell operation, around 10 ampere current, cerium-3 is converted to cerium-4, and around cerium-4 concentration is around 0.7 to 1 molar. We take in that range to have very high efficient destruction of organic. And in the catholyte part, we have nitric acid 3 to 5 molar, and volume is around 1.5 liter. The electrochemical cell is operated at a current of 10 ampere, and organic feeding is currently it is carried out only for 30 minutes. And electrochemical cell of monopolar type with mesh electrodes was used. The efficiency of the electrochemical cell was previously established and presented in many KICH presentations, and the efficiency is very high, nearly 99%. And analysis of organic destruction. This is very important component to understand. As you know, the oxidant that is used is cerium-4 and nitric acid, a powerful oxidant medium. This oxidant medium, when combined with organic compound, organic is completely destructed, immediately destructed. But the problem is the liquid phase analysis cannot be carried out immediately. It needs some pre-treatment. We have to take the sample and suitably pre-treat, adjust the pH, and then we have to analyze. So this is some complicated procedure we have developed in our laboratory successfully for the determination of TOC and CO2. And the gaseous products are analyzed by, as I told you in the experimental setup, we measure the CO2 by passing nitrogen, CO2 analysis, and cerium-4 concentration is also measured by potentiometric redox titration. Next slide, please. So this is the batch process result of the destruction of 250 ppm phenol in batch reactor, and as you can see from this CO2 profile, the CO2 evolution as when you introduce the organic into the cerium-4 nitric acid solution, immediately they are converted to CO2, and within 10 minutes, you can see within 10 minutes most of the organic compound are destructed, and very low amount of CO2 continues to come up to 90 minutes and even longer, because CO2 even at room temperature it is around 350 ppm. So this is below the room temperature. So around 10 ppm or very less amount of CO2 is coming for quite a long period. But most of the destruction, as you can see here, most of the destruction of any organic compound is taking place within 10 minutes, within short duration. And this is the main advantage of this process, and it takes very less time period for any organic. We have tested a number of organics in our laboratory. Next slide, please. And this is the destruction pattern based on COD analysis. Here also you can see, this is also batch process. We are taking 3 different concentrations, 100 ppm, 300 and 900 ppm of phenol. And here you can see maximum destruction is around within 10 minutes. After that it's almost a constant. The increase is very much very little the increase afterwards. Next slide, please. This is the same experiment with different concentrations of phenol, even at higher concentrations of 2000 ppm. The destruction is very fast, and this is based on TOC analysis. Previously I have shown COD analysis, chemical oxygen demand in the liquid phase, and this is total organic carbon of the liquid phase TOC analysis. Even for 2000 ppm we are having nearly 85% destruction within a short period. And this is the comparison how to calculate the destruction efficiency based on CO2 and TOC. TOC gives C by C0 value, that is the concentration relative to the initial concentration. And the same, nearly they are matching the CO2 evolution, the calculation of destruction efficiency from CO2 data and calculation of destruction based on TOC data. They match together, each together within some narrow range. Next slide. And to calculate the kinetic of the process, we have, for batch process, we assume some fundamental concepts. Basically in MO process, the reaction is irreversible, and here one-step conversion. This is assumption we have made that the reaction is one-step conversion. Actually speaking, this is not one-step conversion. Within 10 minutes, n number of intermediates are appearing and disappearing in the system. But it's very difficult to follow the kinetics of each and every intermediate species. So we assume that the reaction is one step, and the reaction is first order with respect to organic, and the forward reaction rate can be calculated by using the simplified pseudo first order reaction. Next one. And this is the kinetic model to calculate the rate of the reaction from the product CO2. Usually the rate of the reaction, as you know well, it is calculated based on the concentration change of the reactant. But in our case particularly, we cannot calculate exactly, we cannot exactly follow the concentration of the reactant with respect to time, because it's very difficult to measure within a short period. So we measure only the final product CO2, and CO2 can be used based on this equation. CO2 can be used to calculate the rate of the reaction, and these equations we use a simple pseudo first order rearrangement of this equation, the integrated form of the equation and differential form of the equation. Pseudo first order we use for the calculation of the kinetics of the process. Next one. As you can see, when the logarithm of CO2, this is the data which I have shown previously from the CO2 curve, that is converted to logarithm of CO2 in millimole, which is plotted against time. See, it clearly shows the two kinetics. It is not a single kinetic, as you understand here. It's a very two distinct regions you can see. The very fast reaction kinetics in the beginning and then very slow reaction kinetics. And this fast reaction here, almost 90% or 95% of the destruction is taking place. If you ask me why this kind of two different nature of kinetics is followed in MU process, in most the process MU process, as you know, this process is highly very rarely investigated, and this is highly patented process, and not much information is available. As we know from the literature, the reason for the slow kinetics is the formation of some short chain aliphatic compounds which resist further oxidation and which is slowly degraded. Like acetic acid, like some short chain acids or short chain aliphatic compounds, they are responsible for the slow nature after this 95% destruction. So immediately it is destructed, and then a very slow kinetics is observed. This is due to the production of some short chain aliphatic compounds which resist oxidation or which undergoes oxidation slowly, you can see. Next slide. So from the batch process, based on the pseudo first order kinetic conditions, we have calculated the K value. As I told you, two regimes we have observed. One is the K1, the first order rate constant, the first regime, and second regime. And we have calculated the fast process and the slow process. We call it as fast and slow process. So we have calculated at different temperatures the K values, the kinetic constants for the batch reaction. Next one. Actually speaking, the usage of the MU process is highly beneficial when you operate only in continuous mode. Batch mode will give you some idea to understand about the kinetics of the process, to understand what's happening, to understand the intermediates, to analyze the intermediates, etc. But the continuous process is very important because here cerium-4 is regenerated again and again in the electrochemical cell, and organic is continuously fed from one tank and organic is destructed. So the main aim of the continuous MU process is to destruct the organics completely and continuously. So that is very important. So we have tested the process in bench scale up to 30 minutes of organic feeding. So this is the evolution, CO2 evolution pattern for phenol. We have observed for continuous feeding of organic. And this is the total volume of CO2, that accumulated CO2 in terms of liters. So this is CO2 in the differential CO2, that is the experimental CO2 observed, this one. And second one, the accumulated CO2 in terms of liter. Next one. So here, as you can see from the previous diagram, it's very complicated. You cannot calculate the kinetics easily. The problems to be solved in this point is how to calculate the kinetics constant in continuous organic feeding mode. This is a very important problem to be solved. Next. So we have developed a model to calculate this kind of kinetics constant for the continuous feeding mode. So the experimental procedure we have adopted for this is a simple modeling for this experimental procedure. So we assume the single step kinetic model. The model is expressed in differential quantities, and here the total time of organic feeding is divided into n small intervals, delta t, during which organic is added as one portion, and VMUO is the volume of the MUO solution, total amount of volume of MUO solution. And next one. So here I can explain you what is a simple model. Though it is mathematical, I can explain you very clearly. So in the step 0, that is without when we added no organic material, in the first moment, the concentration of the organic that we have added in this first moment is delta C. Sorry, this is step 0. The total time, this is the first moment. That is, I am starting the reaction by adding a small quantity of the organic. So the organic, I assume that the organic I have added in that moment is present as it is, and the concentration of organic at that moment is delta C. The next moment I add some more quantity of the organic. So the total amount of organic now becomes 2 delta C. But the organic that is added previously undergoes destruction, and therefore only some portion is remaining in this step, and the organic that is added in this moment is present as it is. So this is the summation step. So this is continued for n number of steps. So this is a very simple concept. Well, it's not complicated, you can understand very easily. It's a very simple concept based on the reaction constant K value. The reaction is proceeding, and we can calculate the difference between the amount of organic added and the amount of organic that is remaining in the solution after reaction. Next slide, please. So we have developed this blue line, this violet color line is the simulated, or so not simulated, this is the model of CO2 evolution pattern we have observed. And these red dots are the experimental points. So you can find a close agreement between this and this. This CO2 evolution pattern is usually tested with arbitrary K values. So we have chosen different K values, and for different K values we get different types of this CO2 evolution curve, and the curve which matches the experimental data we are presenting here. So the curve with good suitability with the experimental data, that K value is taken as the overall kinetic constant of the process. So as I have explained you previously, it's very difficult to calculate the kinetics of the continuous process. So the overall K value, the overall pseudo first order kinetics constant of the process can be calculated only by adjusting the K value and matching the CO2 evolution pattern of the experiment and the model, and calculating the K value from the arbitrary value of the model. Next one. So we are how we select the K value. K value, as I told you, K value we are arbitrarily choosing. How to match it? So K value we are testing for different K values. We take the difference between the K value and the experimental points, and the sum of the least square difference we plot here, and the value with the minimum least square difference is the K value, best K value we take. So this is the best K value. Although we test with several K values, we take this K value as the best one which fits experimental data. Next one. So this is the Eyring plot to calculate the thermodynamic parameters. We are plotting the K value that we obtained by continuous process K by T is 1 by T. From the slope and intercept we calculate the thermodynamic parameters. Next. So delta H, the change in enthalpy, the change in entropy, change in free energy and activation energy we calculate. So this model enables us to effectively calculate the kinetic constant K value for the continuous feeding mode. So the conclusions of the MU process has successfully been tested for various organics, and a maximum destruction of 95% in terms of CO2 production and total organic carbon of the liquid phase was obtained in both batch and continuous organic addition. The simple model is proposed and validated for the calculation of reaction rate constant from CO2 data. The single step model was presented for describing the CO2 evolution during organic destruction in MU process in continuous mode. In the single step model, by fitting the experimental data to modeling, the overall pseudo first order chemistry was obtained. The thermodynamic parameters were calculated. The model predicted a steady state for the destruction process during a simultaneous organic feeding in constantly stirred tank reactor. The results obtained were used for the optimization of destruction process and for further scale in pilot scale. Next slide. So this is you can find this paper is now online. You can see this chemical engineering journal, Mediated Electrochemical Oxidation of the study which concentrates on CN3 oxidation and phenol degradation. This is now available online. Our first paper presented, accepted in journal. And the second one is in water research, and third one Journal of Hazardous Material, and the fourth one is in chemosphere. And this paper is the modeling paper with Professor Lee, who is sitting here. This paper is also very important, which gives some idea about this process, MU process. So this work was funded by MOCIU. Suncheon National University, Province of Korea. So thank you very much for all.
Okay, thank you.